Well, I think we're going to dive in and get moving along, and we'll see if we have a few more join us as we go through, which has certainly happened over the last couple of sessions. And we're going to start off, just want to kind of see who's out there exactly. So if you can just type in the chat, and I know we don't have a ton, so we're not going to be doing a huge amount of waterfalling at this point, but if you just want to put in current role in education and whereabouts you're located, I will kick things off as well here and put in mine. So. And then whenever you're ready, just hit enter. I see mine. I'm not sure if we got principal. Fantastic. All right, wonderful. Okay, cool. So I think one of the things that is interesting at this point in time is given, and obviously experience as a principal and so forth is very relevant at this point. We're dealing with a lot. This year has been very difficult. It's been very challenging. And I think one of the fascinating questions is if we think about the next year and the upcoming school year, what's an unrealistic expectation in this context, especially when we think about the kids that are coming back with, as people are calling it, learning loss or unfinished learning. I'm curious what we think an unrealistic expectation would be for the next school year. I'll give a second for any responses here. Let's see. And Melanie, you are more than welcome to add your thoughts to this. It would be great to see. What do we think some unrealistic expectations might be for next year? And hello to those of you just joining us. Just got a little quick question up here. If you just want to, we're just beginning to talk a little bit about sort of learning loss, learning recovery, unfinished learning. I know in the past I've talked a lot about the different, different ways of thinking about this. I'm just curious about for the next school year, what are some unrealistic expectations? I can see here, tough question to answer. That's I think that's one of the reasons why we've put it up there. That's definitely a really good point. So I'm just curious if you want to type in the chat, what do you think, what are some real interesting, unrealistic expectations that we might have for next year? And I know, okay, Melanie, okay, the fact that there would be no learning gap, I think that's pretty cool. That's definitely, and yeah, making up the learning gap in a short amount of time. And what I was trying to type here is if students are put back to a lot of intervention work, here we go. I think this kind of, hopefully everyone can see that. I think this is definitely something that we're hearing a lot, is that, one of the ways that we traditionally go about trying to help kids maybe with sort of unfinished learning is, okay, we're going to assign them a lot of intervention material. And then, of course, the chances are they're not going to catch up. So, all right, we're going to do something very different here. And we're going to play a game, which may seem like the most bizarre, completely sort of unrelated thing to do, given that we're just talking about learning loss, talking about this idea about how do we get students to catch up. And just, I guess, while we're here, before we dive into the game, I'm curious if everyone just put in, what's your familiarity with STMath? I'm just, if you can just say lots or none or a bit, or I've used it for 20 years, or I designed games for it. Just be really curious to know what is everybody's familiarity with STMath, because we're about to play a game and dive in. So I'm curious as to what people's familiarity is with it. And none is a perfectly great answer. In fact, that's a really good answer. Brand new to STMath. Love it. Fantastic. All right. Thank you, Jonathan. We're starting to use it for the upcoming school year. All right. Brilliant. So great. So this is fabulous. So thank you, everybody, for joining us. So we're going to dive in and we're actually going to play a game, and we'll do it using the chat window. Okay. It's a pretty simple game, and it's going to start really, really simply. But what you're going to see is that the complexity increases in surprising ways. So the objective of this game is very simple. We've got some numbers we can type in up here, and we've got to figure out how we're going to fill this hole in the ground. So I'm going to get everybody to just put something in the chat window, and let's just say we can do this in that typical waterfall type way. Type a number, don't hit enter yet. Once you've typed something that you think that, basically what number should I put in the box is my question. This is a very easy start, but trust me, this is going to get trickier. So, all right, so let's see, hit enter. What have we got? What number do we think should go in the box here? Let's see, what do we think? Oh, we've got 333. Fantastic, thank you. And good afternoon to everybody just joining us. Thank you for joining us. We just got started on playing a game. We've been doing a little bit of discussion about learning loss, but we're starting off by playing a game. Everyone thinks I should put a 3 in this box, and guess what? You are absolutely 100% correct, because when I put 3 in, this little penguin can get across the screen. The penguin's name is Gigi. For those of you completely unfamiliar to ST Math, we're going to dive in and look at it from a lot of different perspectives in the next sort of 50 minutes or so. But right now, we're going to start off by playing a game. So what I want to know next is, you can see now I have 2 boxes up here, and there's also something in the ground. So, all right, what do you think I should type in these? What are the numbers that I should put in these boxes? So let's do this again. Don't hit enter, just put 2 numbers or whatever you think I should put in these boxes. Type that in the chat window. Hopefully everybody can find the chat window. And okay, let's hit enter and see, what do we think? What should I be putting in these boxes? What numbers should I put here? 2 and 7. All right, let's see. So again, nice simple start. All right, very good. So fantastic. Okay, we're off to a winner. Gigi's getting across the screen. Trust me, this is going to get more complex very quickly. Oh, great. I see everyone's starting to join us. Hello, Elaine. Got a few with us now. So we're playing a game. We're doing it interactively. What I'm looking for is for everyone to type in the chat the numbers that they think I should put in these boxes. Now, this game starts very simply, and you're going to see it's going to get surprisingly complicated surprisingly quickly. We've played 2 puzzles a bit so far. Okay, so don't hit enter, but let's just have everybody type in 2 numbers that you think I should put in this box, in these boxes. And okay, let's go. Let's hit enter and see, what do we think? 2 times 3, 2 times 3. Any advances on 2 times 3? No, it looks like everyone's there. Okay. All right. So we get the idea of this game. We're filling in holes in the ground based upon an expression. So now it's going to get a little more interesting. Okay, so now you can see I've got a slightly more complicated shape in the ground, and I need to put 3 numbers up top. So again, let's try this. Let's have you type in, what are the 3 numbers you think I should put in these boxes? And let's give everyone a minute to put what they think. I'm hoping now, maybe not this puzzle, but at some point here, we're going to get some stuff wrong, which is good. Getting stuff wrong is fantastic. So, ooh, we're all jumping ahead here. Okay, so I see we've got an answer. So if everyone wants to hit enter in the numbers that you think. Okay, thank you, Therese. Jonathan, ooh, we've got lots of numbers there. 5, 3, 3, 2. Okay, got it. Okay. So everyone is basically putting something similar here. You guys are just all way too good. Okay, do we have any differences? Oh, we do have a small difference. We've got 5 plus 4 times 3, 5 plus 3 times 4. It actually, in terms of this game, is not going to make any difference. So let's try one of these. Now we're going to get a little more complicated still. So notice now I have 3 numbers up top. I actually have a much more complicated hole in the ground. Don't hit enter yet, but what are the 3 numbers? You don't need to necessarily type in the whole expression. You can if you want to, but what are the 3 numbers that I should be putting in to this puzzle? What do these think? So don't hit enter yet. Let's just wait a moment. Okay, so let's see what we got. What have we got here? 3, 4, and 2. Damn, you guys are just way too good. 3, 4, and 2, Elaine. Okay, 3 times 4 plus 2. No parentheses, Elaine. My goodness, my son would love it. Okay, so fabulous. Let's see what happens here. So notice this is a game that started off where we had to fill one hole by putting in one number. And now notice after several puzzles, we're at the point where now we're able to ask students, which algebraic expression should we choose to be able to fill this hole in the ground? This is actually something we do in 5th grade. We see it again in 7th grade in a slightly more complicated way. So this is one of many, many hundreds of different games, but this is one piece where you can see we can start very, very simply and we can build some complexity. So here's a question then. Let's call these 1, 2, and 3. Which of these algebraic expressions do we think we should choose in order to fill this hole in the ground? Don't hit enter yet. Let's just wait 1 second. If everyone just wants to type in 1, 2, or 3, or if you've got cameras on, you can hold up your fingers, 1, 2, and 3, whichever one you prefer. I do love seeing faces. Thank you, those of you who have cameras on. And okay, so let's see, what do we got? I see that. Anybody want to put something in the chat? Let's see what. Okay, fantastic. So you're absolutely correct. Let's do this one, and I want to get to the net. And I'm pretty certain, given that we got this right, we all understand how to do this. So let's just see where we get to next, because we're able to take this one step even further. So, okay. So here's something a little more challenging. Now, remember where this started. 7 puzzles ago, this was one hole in the ground with 3 blocks, and now it's this. So let's do the same thing. Let's ask 1, 2, or 3. Which of these 3 expression clouds, if you want to call them that, which of these could we use to fill this hole in the ground? Let's think about it for 5 seconds. 5, 4, 3, 2, 1. Okay, show me what you got and put something in the chat. Which one of these do we think we've got? Okay, I see some advances there. Anybody got anything different? I see some 3s. Anybody got anything different from 3? No, we're resolutely sticking to 3. That's it. So 3 will work. That's totally fine. Anybody? And 1. So what's interesting here, thank you, Elaine, is we actually have 2 possible answers here. So great for class discussions, because now, of course, students can see how these things can be done different ways, because in fact, there are 2 different ways of looking at this pattern. It's either, yes, it's 751, 751, 751. So here you've got, okay, I see a bunch of 751s repeated a bunch of times. There's my distributive property. And then I've got this extra 7 on the end. Or, of course, you could look at it as I've got a 7 at the beginning, and then I've got a bunch of 517, 517, 517, 517. And again, we can get students to engage with this, and then they build this out. So actually, maybe I will just skip here just for the sake of it. And just FYI, something we have coming up new for the next school year, students actually have to build their own expressions. So something that we're gradually moving towards here is where the level of ideation is even stronger. Okay, so great. Thanks for engaging with that. So now I have another question that I'd like to ask. And don't hit enter. Just let's have everyone type for a minute about what are the benefits of playing something like this for students? And I think we could even add to that. What are the benefits of playing a game like this for students in the way that this works? For let's say students who are even struggling to be at grade level, students who may be experiencing learning loss, let's say, for example, they're coming into middle school. What are the benefits of playing a game like this for students? So let's just type some stuff in. I'll count in my mind maybe 15 or 20 seconds. And let's see what are the benefits? Why is that a big deal? Why is it useful to play a game with a penguin? Why on earth is that even remotely helpful? I promise I'll stop talking so you can concentrate. Thinking about stuff. Okay, we'll give another 5 so seconds. Okay, so hit enter. Let's see what have we got. What are the benefits here? Okay, thank you, thank you. Ooh, I need to extend my chat window. Getting too much. Okay, hang on. I just make it bigger. All right, there we go. Fabulous. Um, all right, fantastic. Engaging, applied thinking, focus. Okay, love it. Let me go through these because there's a lot of good stuff here actually, and I want to sort of really sort of respond to what everyone said here because there's a lot of good stuff. Applied thinking, low risk. Now, we didn't see what happened when we got stuff wrong. We'll see that in a moment. But you're absolutely right. This is very low risk. Notice this is the students who would be playing this. If they get something wrong, they see why it's wrong and they get to do it again. There's no risk. Their percentage doesn't go down. They don't sort of, there's nothing detrimental that happens. Love this develop reasoning. That is exactly, we're going to see a lot of the neuroscience in a little bit. We'll look specifically at how does this stuff develop reasoning, because you're absolutely right. Visual to symbolic, absolutely. Thank you very much for that. That's totally key. We see here, this is heavily visual and then it gradually sort of, moves to a more symbolic kind of place. It is challenging and interactive, absolutely. Engaging, yes, kids do like it. Using the game is beneficial to students, taking the pressure off. Yes, absolutely. And I think, and I like this as well. This is a real critical idea here. Focusing on patterns and modeling. Now, if you think about the traditional way that students perhaps get introduced to expressions in middle school or even high school, I taught high school math myself, that is not how students generally get introduced to working with expressions. It's a little bit more of a tedious process and it has very little meaning for them. So the fact here that we can get kids through playing a game, we can get them to engage with sort of building an understanding of how expressions work and so forth is a big deal. So we're going to play some more, but before we go there, I just want to kind of come back to this whole topic of learning loss. One of the other key pieces that you saw there, now we saw, I think there were 8 puzzles altogether, and they started off ridiculously simply and ended up actually not ridiculously so, but relatively complicated. Now, a student wouldn't make progress through things. There wouldn't be that much of a leap over 8 puzzles. They'd see a whole bunch of stuff at each kind of level, as it were, within STMath. But some of the big ideas here really do apply, and this is a big piece of it. Let's say you've got a student who is struggling with even the concept of a variable, or they're not on grade level with these kinds of concepts. Notice how that started way below the place where they need to be. It would pick them up. They would kind of get, even if they were approaching that significantly below grade level with some significant amount of learning loss, it doesn't matter. We can scaffold down and we can bring them to the on grade level mathematics that they need to do. And interestingly, we have one of the recent studies with STMath actually looked at students who took an additional assessment. They took something else in their district, and the assessment decided, were the kids on grade level or different stages. And we were able to look at them, as they made progress through STMath, what were the sort of average number of attempts they needed on the different objectives to achieve that content mastery? And obviously kids who were on grade level, they got through it with a certain number of attempts. And you can see that different objectives within STMath require, some are more difficult than others. The content's more tricky or something about it is more tricky. But what's interesting here is even when kids were assessed externally at being one grade level behind, meaning they were, in this case, they were all in 4th grade. It wasn't like they were doing different content. They were all in 4th grade. They were all doing this content, but they were assessed at being at different, sort of stages. The kids who were assessed at grade level behind, they were still able to get through and achieve mastery. They just needed more time on that problem-solving learning process. And really excitingly, even kids who were 2 grade levels behind, the same thing, and even kids who were 3 grade levels behind, but they did need kind of double the amount of time, which is fine. So the point being here that when you design stuff that is engaging and kind of takes kids from that real sort of fundamental understanding and brings them to the on grade level stuff, you don't have to put kids way back multiple grade levels just because their assessment kind of says this is where they are. you can keep them on grade level. They just might need more time with that on grade level content. So interesting piece there. All right, let's play another game. So this time we're going to try it a little bit differently. And I hope this works for everybody. I did mention up front, if you have a phone handy, that's awesome. If you don't, I know I was supposed to put a link in the chat, which of course I've now totally forgotten where it is. But if you don't have a phone handy, maybe let me know in the chat and I'll see if I can find the link. Because we're going to play another game and I'm going to have you scan a QR code. And hopefully if you turn your phone like horizontal, it should play okay. STMath is not really designed for phones, but it will work on them. So fingers crossed the experience will be okay. So, but it's a fun thing to try and do. So, all right, this time you're actually going to do the hands-on playing, okay? So let's try it. Let's see, you should, hopefully that QR code, let's see, is that scanning? Let me see, or is some of it missing? Hang on a minute. I might need to, no, I think some of it's missing. Wait 1 second, I can fix this. I can just make it slightly smaller. Wait a second. Yeah. Okay, no, that's not working. Okay, let me just do this. Go back here. No, stop. Okay, let's try that again. Hopefully now if you scan this thing, there we go, that works now. You should be able to open up on a phone. You should get this game pop up on your phone. Gigi might walk a little bit for a minute or so. I think on phones it's a little weird, but hopefully you can get this. If you can give me like a visual thumbs up or okay, all right, this is good. Okay, you might find it easier if you turn your phone horizontal. I don't know. Sometimes the play seems like it's okay. All right, the goal of this is pretty simple. You can drag this around, and once you put it to wherever you think it should be, you're going to try and figure out how you're going to get Gigi to this platform. So for example here, I drag this out a little bit. I can click this and Gigi went a little bit fast. So let's give you a minute or two. Let's have you play through this and see what we think is going on here. Talking about patterns and modeling. Is there anybody who was not able to get the game functioning in some way? Right, I'm going to take that total radio silence as a yes, we've all got it working. And hopefully everyone's going to be able to figure out how to get Gigi across to this little rocket. I will slowly do these on the screen just so for anybody who's watching on a recording, we can actually see what's going on here. I'm not going to talk a whole lot about what I'm doing because I want you guys to have a chance to play this. And I'm hoping that you make some mistakes. In fact, I'm going to make some mistakes. Let me do it because we'll see precisely what happens when we get something wrong. Let's say I don't quite get how it works. Just get to do the same puzzle over again. Yeah, this actually works quite nicely on my phone. It's kind of cute. Okay. Now, the question I'm going to ask once we finish this, or once we kind of get through a bit of this, is what is the math? So just be thinking as you're going through here, what math is this kind of getting you to think about? What is it kind of getting you to do? And we'll see what the thoughts are. But you don't have to answer that yet. You can just think about it. And if you finish the level, maybe just type finished or something like that in the chat, just so Have some idea of where everyone's at. This is a very interesting puzzle. The one that I've just got on my screen right now is where this gets really interesting. It's also the one I'm doing on my phone. Okay, I don't see any finishes yet, so no worries. We're going to give everyone a little bit more time. Totally fine. Think about the math. Think about what's happening here, because there's a lot going on. There's a lot of interesting things happening mathematically. And you're actually lucky I gave you the version with the unit blocks in it, because there's a version of this without any unit blocks, which is really, 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 really interesting. Okay, I'm going to give us all about another 30 seconds with this. And then let's see. Doing all right. So 10 more seconds. I'm just going to finish this one here. I got it wrong. All right, so fantastic. Okay, so I don't see any finished yet, but hopefully we got some significant progress. So start asking a few questions here. So fantastic. All right, thank you, Melanie. What mathematics was going on in those games? What was happening there? What was the math that was basically present in that? And again, maybe don't hit enter yet, just kind of type in your thoughts as to what was the math, what was happening when the students were playing through those games, and maybe also what was the math, what grade level is that typically taught? That would be another interesting question. And okay, so let's see what if you want to hit enter, what math, what grade level, what do we think about this? Good job. My wait time is really well rehearsed at this point, isn't it? What have we got? So what math do we think is happening in these games? When do students typically see that kind of stuff? Maybe even do typically students find it easy would be another interesting question. So if you want to hit enter and send your thoughts to the chat. I don't see anything in the chat. Does anybody put anything in the chat? Okay, there we go. Fantastic. Ah, yes, hit enter. Thank you. Okay. Gosh, my eyes are not good enough. Does that say sixth or eighth, Elaine? Because I cannot. Sixth. Okay, six. Okay. Okay, positive and negative integers. Fantastic. All right. And thank you, Teresa. Yep, absolutely. So adding and subtracting integers. In fact, we actually got a little bit even more than adding and subtracting integers, because I don't know if you got as far, but there was actually a little bit more there as well. In fact, the game will go a lot further than that too. So yeah, so basically that was a game that basically does this stuff. And very typically, this is a subject that is taught something like this, right? My son, actually, who is in fourth grade, but is sort of, I don't know, given some, he's sort of being rushed through some stuff which I'm not totally a fan of. But anyway, it was being taught this recently and basically had worksheets for every single section on this page. The method of teaching it was, okay, we're going to teach you these rules, and then we're going to give you a whole bunch of worksheets to go along with every single section. And the theory is here that if you practice each of these bits enough, you will then basically know exactly how to do this, and you have now done math. And what's extremely problematic is that this is a very typical approach to this. There are obviously lots of posters. I'm sure everyone's seen all the kind of posters that teachers typically have up in their rooms for this type of stuff. And the problem is here that these rules, even, I mean, I understand why, I understand where, and I get it, but integer addition rules, if the signs are different, subtract the numbers. I mean, first of all, there's a disconnect right there. This is about addition now. Subtracting, keep the sign of the larger number. And it's sort of like, okay, if it's plus and minus, we do this. If it's minus and plus, we do something different. The idea somehow that you're going to basically memorize these things is obviously quite problematic, because there's a lot of stuff to remember here if that's the way you're going to approach it. And this is very likely, this is the type of stuff that for many kids results in math anxiety. This is where because they don't understand how it works, they end up just trying to memorize their way through these things, and it leads to a lot of problems. And one of the challenges here is this in no way bears any resemblance to the way that the brain actually stores information, thinks about information, or even understands math. And in fact, this bears no relation to the way that mathematicians think about math. So the fact that a student could kind of be trying to memorize their way through this and then sort of come to the conclusion, well, I'm just not a math person, is not surprised, because math people don't do it like this. And when we think about the brain, the way that the brain would take this information, it says, okay, what are the really key big ideas here? And it's not so much a question of learning these big ideas separately, it's learning these big ideas and all of the connections between them. And what's interesting with a game like that, and we're going to see how that sort of develops, is we can reduce all of those integer rules down to a couple, or in fact, in this case, three very simple big ideas. So one of the big ideas is that basically adding stuff together is literally just joining things. So this idea of joining being adding is one of the ways that mathematically we're able in STMath to kind of look at this and go, okay, here's a big idea. Let's make sure we get this. Then another really big idea is this idea of multiplication as some kind of area. The idea that you can take basically two numbers, a length and a width, or whatever way you want to describe it, and create an area out of them, and that can be measured. So the idea that multiplication can be an area is another big idea. And then, of course, something that you may or may not have seen, one of the other really critical ideas is this idea of when you're making something negative, it's basically the same as performing some kind of flip about the origin. And this can happen multiple times. You can flip something to make it negative. If you're multiplying it by a negative again, it just flips back to become positive, and so on and so on. And with these three simple ideas, all of the integer rules. And in fact, with this game, we can also go into division. We can even do exponentiation, actually, with this particular one. But with these three simple things, we can go all the way and handle all of these kind of, the things that are typically memorized. We can actually get students to do them with understanding rather than doing them through memorization. And this is something we're able to do consistently through STMath, is we're able to use these kind of visual models to underpin that conceptual understanding of the mathematics. And to a point that Melanie made earlier, we don't just work in the visual space. Yes, STMath begins visually. We scaffold down, we make sure students can sort of understand this from a really fundamental level. But then we actually transition to this point where the students are working symbolically. So like this, they will now be solving the exact same symbolic problems that they will see anywhere else. But this time, when they solve them, everything animates in terms of the visual models that they're now familiar with. And you can see here is positive and negative integers, all done through the medium of these three very simple ideas of, okay, if we're adding things, we're joining them together. If something's negative, it's basically a flip. And this other third idea then of this idea of multiplication being kind of an area model. And through those three really simple big ideas, we're able to handle all of positive and negative integers. And actually, I didn't do it here because gets really a little more interesting. But we can even do division through this model. We can even do division of fractions through this model. There's a whole lot of stuff we can do. And here, multiplying by a negative number, it's just that flip. And of course, we can multiply a negative by a negative. Why is it positive? Well, because when you take something negative and you multiply it by a negative, it means you have to flip it again. So all of these things now have meaning, they make sense, and the students understand what it is that they're trying to do. Fundamentally, that's what we're trying to do with STMath. We're trying to get students to the point where they can understand things. And it does look very different. One of the questions we get quite regularly is kind of this idea of like, wow, this looks like this sort of bizarre game-based thing. How on earth is that teaching math? And when you actually look at what students are doing, you see that they're actually having to do some quite odd-looking things. I walked into a classroom 11 years ago. I was a high school math teacher, then I worked for Los Angeles Unified as director of math for many years. And I walked in and saw kids solving these problems. And what was so fascinating was the depth of thinking that I saw occurring for all these kids at the same time. And that was one of the things that for me really sort of made me realize I was seeing something quite powerful and quite unique. And in fact, I actually left my job with LAUSD not long after and decided to go and build games with STMath. And in fact, that positive and negative integer game, which is called Jelly Blocks, is one that I built, I don't know, quite some time ago, actually. I forget when it was exactly. All right, so one of the interesting things then is that despite the fact that STMath looks nothing like other math programs, despite the fact that it's, to some people it's like, how on earth is that even teaching the kids math? Because of the way that we approach it, sort of math learning from this real fundamental conceptual perspective, and we build from that visual to the symbolic, we actually see impacts at a really interesting scaled level. So, the What Works Clearinghouse defines a sort of substantially important effect as an effect size between 0.25 and 5. And in a massive study that came out a few years ago, looking at actually 42,000 kids in a control group and 42,000 kids in a treatment group, across all grade levels. This was something, all grade levels that take assessments. We were able to sort of achieve effect sizes in this very important range. And the interesting thing here is obviously there are plenty of programs that have effect sizes that are basically negligible, and there are many where the outcomes are actually detrimental. My daughter, who's in first grade, was playing something the other day where, if you make a mistake, you see that your percentage goes down. And I could just see her math anxiety, this anxiety kind of rising as she's playing this thing. This is actually detrimental to the learning process. So the fact is here, we can actually give students things that measurably can actually really build their confidence and actually build their ability to perform mathematically in an interesting way. So I taught for many years. This is a great question. It's something we ask a lot, this kind of idea. How do we teach? How should we be teaching? And one of the things that STMath does really well is they basically put this question to one side. And in the 90s, in the University of California, Irvine, they basically decided, we're not going to answer this question. We're going to answer something else. Instead of how do we teach, we're going to ask the question, how do we learn? And more specifically, what if math could be taught the way the brain learns? And fundamentally, that's kind of the ethos, the design principle behind STMath. We're trying to figure out how can we teach this in a way that actually matches the way that the brain learns. So we are going to play, I'm going to skip this one for a minute. We're going to play another game because I think this will be somewhat new to some of the people. This will be somewhat familiar to some others on the call, but we're going to play one more game and then go through and dive into a little bit of neuroscience. So we understand what's happening with STMath. We've got to figure out how we're going to get Gigi across the screen. So we can do this again. I mean, maybe we can do this visually. We've interacted via the chat. We've interacted via you guys actually using your phones to play a game. If we can get everybody to turn their cameras on, I think everyone here has them, then we can even do it with fingers over the thing, because that would be a third mode of interaction. And that'd be great. And that'd be fantastic. So if that's possible, that would be awesome. No worries. If it's not, you can type in the chat. So we're trying to get Gigi across the screen. You can see here, we've got 6 things we can do, 6 ways that we can move and manipulate this penguin. And we need to choose 3 of them. We can choose any 3, any order. We can repeat them. We can do whatever we want to do. And there are multiple ways of solving this problem. So let's see, let's again do this like before. Let's take a minute, let's think about it. And then I'm going to count down and we'll see if we can just put up fingers or hit something in the chat. So 3, 2, 1. All right, what have we got? Give me a number. What number do we want to do? 2 and 3. I see disagreement. Okay, fantastic. All right, nothing like a bit of disagreement. I like it very much, Jonathan. I see we have another guest with us today. That's fantastic. I love it. Maybe he's a little small to play Gigi, but that's all good. We like him. Like them. They do like watching this. All right, so let's see. We got 3 and 2. I'm going to go with 3 just because it's less common and other people. Any one of those 6 would have worked, by the way. Okay, so now let's visualize what happened there. What would be a good second move? Let's think about it for a minute, and then again I'll count down, and let's look for a number between 1 and 6. Okay, 3, 2, 1, go. What do we want to do? Ooh, sorry, I missed that. Number 1. Okay, let's try number 1. Okay, now notice Gigi is not moving. It's not because this is wrong. This could totally fantastic. We just got to visualize the entire thing in our heads, and then we get to see what happens. All right, so okay. Last move. What do you want to do? I love seeing the hands moving. This is fantastic. We love it when kids do this. We actually give them things sometimes to do this because we want what we call physical ideation, when basically what's happening in here is being represented out here. It's a powerful thing to do. So last move. What do we think? What's that final move? Let's go for it. Let's see. What do we got? See some uncertainty. See thinking. I see puzzlement. This is good. 5. All right. That was the least confident 5 I've seen, Emily, but that's fine. Let's see what we have here. All right, 5. Fantastic. Let's try it and see. Okay. Oh, fantastic. All right. Okay. So Gigi got across the screen. I am gonna just let's just for context. This is a game we can get kindergarten kids to solve, certainly first grade students. Now, they don't start with 3 of these moves. They start with 1. They begin their spatial reasoning, and then 2, and then 3. And one of the interesting things here, it's not just a few kids who can do this stuff. All kids, if given the chance with these kinds of tools, can build the spatial reasoning necessary for this. And there are tons of ways of thinking about it. Like I said, there are actually I think somebody did this the other day. Let me just get one wrong deliberately. Let's just see what happens when we get this wrong. And you can see I got it wrong. Gigi goes back and I get to try it again. So I think somebody mentioned this earlier. This is a low stakes way of learning, and it is the student who's engaged in this learning process. And what's going on here from a neuroscience perspective is something called the perception action cycle. And this is not it's not a some student thing. This is not something that we created at ST Math or a mind research thing. This is a commonly understood piece of neuroscience. All human beings use the perception action cycle multiple times a day. In fact, all mammals use the perception action cycle, and generally speaking, most students fit into some of those categories. So the idea here, this is something all kids can do, and it's something we can use then to actually build fundamental math schemas, as we call them. So it works a little bit like this. Anytime you're confronted with a problem, doesn't matter what that problem is. In this case, how do I get a penguin across the screen? We fire up what we call our existing schema. Whatever prior knowledge, whatever we've got in here, it fires up and it causes us to make a prediction. Like, oh, here's what I think will happen. And then we take an action. Based upon that, we take some action. In this case, we choose some moves in the game, right? And then the game animates that out without prejudice. It just animates it out and shows us what our thinking sort of does. And in this case, whoa, Gigi got across the screen. We perceive it. And then in the brain, in the hippocampus, a little piece right in the middle of the brain, it's like 2 little seahorses, one on each side. That prediction that we made is held there. It's like literally just there waiting. It's not going to wait there forever, not that long, like maybe 20, 30 seconds, that sort of time frame, maybe a little bit longer depending on the context. Certainly not over the weekend while your homework gets graded. That is not the time frame we're talking about here. It's pretty quick. Wow, he's loving this. This is great. Fantastic. Um, so that that prediction that you made is held there, and then the perception of what happened comes in, and in the hippocampus, these two things get compared. Here's what I thought was going to happen. Here's what I see actually happening, and boom, those two things get compared. And in this instance, they match. Gigi got across the screen. It worked, and your hippocampus sends a signal to the schema, and it basically grows it. It makes it stronger. So the next time you see a similar sort of problem, similar situation, your schema is now even more developed to be able to solve that problem. This is how we build spatial reasoning schemas, how we build um, proportional reasoning schemas, and we can use it to build number sense, numeracy, fraction number sense, all of these things. We can build these schemas using this perception action cycle. And in fact, for small children, this stuff is in action all of the time, like thousands of times a day as they start building their schema of the world around them. But really interestingly, we don't only learn when we get something right. And let's just sort of rewind this a minute, because really fascinating things happen actually when we get something wrong. And I know one of the comments earlier, I think it was Elaine that you said this idea that when students, one of the benefits of playing a game like this for students is that it's kind of like a safe space in which to get stuff wrong. And it's such a critical thing, because a major, at least half of the learning process happens when you get something wrong. So if you don't feel like it's a safe space in which to operate, basically a major part of your learning process has been removed. So for example, if you're doing problems and you're seeing a percentage going down and you're starting to freak out because like, oh, I'm getting it wrong, and you basically turn off from that and you're like, I don't want to play this anymore. It's cutting out this massive part of the learning process, because this is just as important as what happens when you get it right. In fact, to some extent, you could say it's even more important. And this perception action cycle, by the way, this is really a survival technique. This is why all mammals use this. This is how we make maps of the world around us. This is how we find food and remember where it is and all that kind of stuff. And getting stuff wrong is an important part of surviving. So it's a major part of this cycle, and it's critical when we're learning math too. So it goes a little bit like this. In this case, we take an action, we choose some moves in the game animates out without prejudice, just shows you what you've done, and you perceive it. And now into the hippocampus, here's what I thought was going to happen, here's what I see actually happening, but this time they do not match. And now a different signal emerges, and it says to that schema, that wasn't so good. So basically, it deprioritizes it, meaning the next time you see a similar problem, that's much less likely to fire up. So this is how we address misconceptions. But very importantly, that's not it. When you get something wrong, your hippocampus sends out a second signal. It sends out something called theta waves that kind of basically pulse from the hippocampus. I forget the exact frequency, and it's not exact. It's over a range, but it sends basically out a pulse, and it puts your brain into kind of like a learning state. And we've all had this moment. You try something, it didn't work out the way you thought it was, and you get this little moment of like, huh, this little curiosity, and that is literally theta waves emanating from your hippocampus, basically saying to your brain, you need to learn something new. So that process of getting something wrong triggers the act of the brain to say you need to learn new schema. So it's a critically important part of the process. And like I said, if we're basically teaching students in a way that kind of implies mistakes are bad, just do everything right all the time and it'll be great, or don't think about it too much, just get it right, you're cutting off a huge part of that learning process. It's such a critical piece. And all the work of people like Joe Bowler, this idea that students are going to learn so much from making mistakes. This is the neuroscience that's behind that sort of idea. It's an absolutely fantastic idea, and when it's done well in practice and implemented in classrooms or implemented in a program situation like this, the learning effects of it are really profound. So, all right, one more question. I see time is ticking along here. It always does. I always talk way too much, but that's just the nature of these things. So, all right, one more question about academic discourse. So, and we can just put in the chat, just go for it. We don't need to wait. I'm just curious what people think. What's the purpose? Why, especially, and I'm really thinking here in the math classroom, like what's the purpose of academic discourse in the math classroom? I think is the key, because there may be subtly different purposes depending upon the context. But I'm curious what we think. What's the purpose of academic discourse in the math classroom? I'm going to put in I have heard many times. Fantastic. All right. Awesome. Okay, great. Lovely. So nice range of stuff there. So giving students the language to use, sharing thinking, listening to others' strategies, build academic language, solidify what you know, compare and justify. Wow. I think actually that is that if I was to say what are the purposes and list most of them, that would pretty much be all of them. So that's awesome. And I think there's an interesting thing here. And then Elaine, negotiate meaning in our minds. So yes, that this kind of listening to others, solidifying what you know. So one of the fascinating things, yes, academic language is one thing that can emerge from students engaging in academic discourse. But from a neuroscience perspective, academic language is not the real purpose of academic discourse. It's almost like an optional benefit. It's something that comes out of it, and giving the students the right language to use is important. It's helpful for them to be able to sort of recognize it and see it. But one of the interesting things when we look at the brain, um, there are many sort of learning structures and learning cycles in the brain. We're looking at the perception action cycle centered around the hippocampus and how that kind of works. And one of the other critical sort of learning mechanisms in the brain is the stuff connected around language. But the real big deal of this is not so much around the academic language, it's really around this idea of sense making. And Elaine, I see you said negotiating meaning, and this idea hearing what other people think about something, um, solidifying what you know, that's really the key. And yes, the language obviously is really helpful for that, because if you can't understand what somebody's saying, well, there's a limit then as to how much you're going to get. So all of these things are key. But the key is, how can we use academic discourse to really help students make sense of stuff? And I think there's so many versions of this online, but I think we've all probably had this experience, this notion that, you know, if you want to learn something, you can read about it. If you want to understand something, write about it. But to master it, if you need to teach it. And so much of that comes from this idea of when you're teaching it, you kind of have to explain it over and over and over and over again. And this idea that by talking about something and having to constantly try to think about, okay, how can I justify my reasoning or explain my thinking? By doing that, I actually build a really deep sense of understanding. I make sense of it for myself. Is very, very accurate. It's something we see a lot, and I guess there are multiple sources for this one. This was one that I came across. So one of the things that we do in STMath, then sort of getting to the practical points, like, okay, great, that sounds fantastic, great, academic discourse can do all these things. So we actually then have tools. Yes, there's a game-based component of STMath where students play and obviously learn perception action cycle. They'll do about 3,000 puzzles in a year as they move through that. So there's a lot of learning that's going to happen there. But we also have tools then for the teacher to bring into the classroom, specifically what we call puzzle talks, where, for example, you know, here's one connected to fractions and so forth and so on. And for the teacher, we will have literally down to, here are some questions you could ask, here's the stuff we can do. And they're centered around specific puzzles that teachers could bring and put up on a projector or something like that. Play, have the students talk about how they're solving them. And this opportunity for the students, not only to play the games themselves, but then to actually sort of collectively play the games, if you like, and share their thinking and hear from other people about how they solved it, massively helpful and a real, you know, real key part of that kind of learning process. So as you can imagine, you know, the other thing is, because there's a game at the heart of it, it's something that's quite easy for kids to talk about. There's something very tangible for them to talk about, which is nice. So these things are obviously quite widely used. All right, going to wrap with a couple of things. Big picture here. This may have been a slightly odd look at STMath for those of you who haven't seen it before. Normally we do something a little more structured. This is actually the fourth in a series of sort of discussions that we had. So we've kind of looked at things from a number of different ways, and you've kind of seen the the slightly different way we had of putting it together at the end here. But hopefully some of it kind of made sense and gave you pause for thought about what we're doing. So just to put all that in context, you're probably familiar with charts like this. They're useful for looking at math content and math tasks or curriculum in general. And I've seen them called rigor relevance charts or quadrant D charts. And the idea being you're looking at the tasks that students have to engage with. And you're saying, what type of thinking do the kids have to do? Is it basically memorization, or are they having to do sort of critical, high level creative thinking? Similarly, what kind of questions are they being asked? How are they being asked to apply the learning? Is it basically just routine questions, or are they being asked to solve non-routine problems? And the implication is obvious. We want students spending a lot of time up here, right, using creative thinking to solve non-routine problems. The challenge is that the vast majority of curriculum materials, doesn't matter whether they're online, doesn't matter whether they're printed, makes no difference. They fall very squarely in here. All of the stuff that is basically, hey, we're going to do a diagnostic assessment, figure out what skills you can't do, tell you how to do them, and then give you a bunch of practice on it. That is literally the definition of falling in this quadrant. And that pretty much sums up most approaches to learning loss, is to kind of just do more of this. And the problem is that as we've kind of discussed, it doesn't match how the brain stores the information, and it's obviously not very effective. The other challenge then, of course, is that if you want to teach kids up here, there are plenty of really interesting curricula out there that do all sorts of fascinating things here. Joe Bowler's stuff, obviously, the Stanford's put out a whole ton of good stuff, but a lot of it tends to be word problem oriented and very language heavy, which means for many kids, that's a heck of a barrier to this space. So for many kids, they never get a chance to even do the thinking because of the language that gets in the way. So one of the things that ST Math can do so effectively from pre-K onwards, pre-K all the way through 8th grade, we're able to get kids into this space using creative thinking, critical thinking, solving problems, solving non-routine problems, continually having to sort of figure out how to make things work without that barrier of language. Once we've got them into that space, we can add the symbols, we can add the language, we can have discussions to add the academic discourse to add the academic language. But first and foremost, we need to get the thinking happening in this space. And that's one of the big things we can do. Okay, I think we're just about there. I'm going to skip this one because, just because. All right, it's 1:59, and I want to thank everybody for being with us. So last final closing thought. If this was the old way of teaching math, this idea that you just need to be able to do it like a machine, what we're really about here at Mind Research is figuring out ways. We want kids to understand this because we need them to be the ones who are going to actually build the machines. That's kind of the modern world, really, that they're living in. So I want to say thank you all very, very much for joining us. It's been a real pleasure. And I think there's a survey that Melanie will probably email out at some point. So if you see that and you've got questions or other stuff, please don't hesitate to put that on or reach out in some way. We are more than happy to answer. So thank you all very much. If I'm looking over here, it's because you guys are over here. So thank you so much for joining us. It's been a real pleasure.